Hi everyone. We'll start with a look at the content. First, we'll have a definition what machine-to-machine security is anyway. And afterwards, we'll have a look at some attack vectors which can be used to attack machine-to-machine communication scenarios. And here we'll have a look at attacks over the communication channels that are used for the communication. And also we'll have a look at physical attacks on the endpoints. The endpoints of machine-to-machine communication are usually embedded devices. Yeah, we'll have a look at this thing. Also, I will show attacking some actual machine-to-machine setups with the weaknesses, the attack, and what impact this had. We'll have a look at mitigation strategies. And finally, there's a short summary. So first thing, what's machine-to-machine security? I Gutenberged this definition from Wikipedia. Machine-to-machine refers to technologies that allow both wireless and wired systems to communicate with other devices of the same ability. But in this talk, I'll have machine-to-machine with a wider scope, not just machine-to-machine, but also machine to vendor or to the maker, which is nowadays a bit more common because it is used for remote firmware updates and such stuff. So you'll find this more than a strict machine-to-machine communication. But the name is basically the same, at least for the network operators. They also call this machine-to-machine. If the communication is between a machine and the vendor or the maker. So machine-to-machine communication is, as the name implies, between two machines, which can be seen here. And those machines can either communicate directly or via a common network from the vendor. Those machines have embedded systems, so they have tiny microcontrollers in them. And here we will focus on systems that use IP communication. So there are also other systems which are usually a bit smaller. We won't have a look at those because they are not so interesting at all. Yeah. Okay. So some examples for machine-to-machine communication. The first example that comes to mind is the smart grid applications. For example, you have the smart meters and some metering and controlling stuff. There are also other metering applications like for heaters and so on, but they are usually not so IP-based, while smart meters are often IP-based. Then there's vending machines, for example, ticket vending machines and such stuff. Those can be updated over the air for new price schemes, and also they can report if they are out of tickets or change or anything. And there are industrial control systems and machines. Also there's traffic control and motor vehicles. And I'll also include here entertainment devices, set-top boxes and home appliances that talk back to their vendors or makers, though they are not really machines in that sense, but from a communication they are quite similar. M2M is basically a fancy buzzword because those communication things have been here for quite some time. And there have been embedded systems with network access for years. For example, pay TV set-top boxes have integrated modems for quite some time. And if you had a closer look at the firmware of those devices, you could find dial-in numbers and dial-in accounts in the firmware. And then you could dial into the network of the vendor and have a look around. So this is basically the same thing. Now there's just a lot more devices because those machine-to-machine communications are a lot cheaper nowadays. You can use GSM or Ethernet or something like that. And also there are devices that can do some actual immediate physical harm, which pay TV set-top boxes and PCs normally cannot do. Okay, communication channels are basically Ethernet or wireless LAN. Then there's mobile network, for example, GSM and 3G, and other wireless or wired networks like Zigbee and such stuff. The wireless things are mostly in the ISM band, and we won't cover any other than the Ethernet, wireless LAN and mobile networks in this talk, because the most interesting and the other are usually, again, for smaller systems and not necessarily IP-based. So first point, Ethernet and wireless LAN is basically quite simple, because one can just write the usual exploits to compromise those devices. Those tools are in the wild for years now, and you know those tools, I guess. So, but also do the manufacturers. They know that anyone can do some wireless LAN hacking, that VPA cracking based on word lists and stuff. So they add an additional encryption layer usually, which is SSL or VPNs. And so if one doesn't find an exploit to attack the actual device, one cannot easily break into this communication channel due to the added layer of encryption. But this additional layer of encryption also implies that there are some secret keys and certificates stored in the devices. And this makes the devices an interesting target to attack. And here we'll later have a look at physical attacks on those devices. But first, a more interesting thing is mobile networks, of course. So I won't say any more about wireless LANs, because this is mostly pointless. There's enough documentation already. So those mobile networks are mostly GSM and less 3G yet, because 3G modules are usually a bit more expensive. Also, they consume more power, and the 3G coverage isn't that good yet. And also, in most applications, you just don't need the bandwidth that comes with 3G. So GSM is a better option here. And you can use those modules in 3 configurations, basically. That's circuit switched, so you can dial a fixed number to the vendor, for example, and yeah, basically dial in to the vendor via a data connection, similar to voice, but just a data connection. Then there's SMS-based communication, which makes sense for rare events and notifications, so the device can stay connected to the network, but wait for some events and then send or receive an SMS and react on this thing. And of course, there's packet-switched communication, which is basically GPRS. And this is, I guess, the most interesting thing, because here there's IP communication going on, and this is the most interesting, I would say. So contrary to wireless LAN communication, there's often no extra encryption with those GSM and 3G communication modules, because GSM is already encrypted, so no one can hack this. Yeah. And so how can one attack GSM communications? This is also a topic that's been discussed here at the CCC Camp and some other events before. There's basically the passive sniffing and attacks on cryptography. For example, the A5 encryption algorithm that's used for GSM communication, that's used for dial-up and SMS, is broken. You know this, and though I'm not sure if the current tools will work on data connection as well. I haven't tested this yet, but well, this is easy to find out, I guess. Next thing is GPRS. Here there was a talk from Carsten Nohl on the first day regarding GPRS security. He did show some actual attacks on the encryption, so the GPRS encryption is more or less broken as far as I understood. And so this is an issue, and one can use this for eavesdropping, so passive sniffing, and but well, that's nice, but you probably want to send some own data either to the device or to the network, or better both. So this is where a rook BTS is your friend, and there's OpenBTS and OpenBSC. Both are also a topic here at CCC events for quite some time. And so regarding the rook BTS, the first step is to identify interesting devices, and this can be done via the IMEI. This is the serial number of the mobile entity. The mobile entity is basically your phone or a GSM module or something like that. This IMEI number includes the type allocation code, the tag, and this code identifies the maker and the model of this particular mobile equipment. And there is a public tag database from Colin Mulliner. You can download this database and use it offline. And so if you see an IMEI, you can have a look into this database and see what particular device this actually is. And depending on that, you can decide if it is interesting to attack, because you can see if it's a usual cell phone or if it's some kind of GSM module that is used for machine-to-machine communication. So once you identify those interesting devices, you make this device join your BTS. And here you'll find some devices that join foreign networks automatically. But some other devices need a spoofed real network. So they will only connect to the home network, and one has to spoof this home network for the devices to connect. And well, this is probably some kind of illegal, so think about it before doing this. And anyway, once you get the device connected, it basically looks like this. You have the original vendor network with other devices in it, and you have your network with the device that actually connected to your network. So the device is then isolated from the real network, and it cannot necessarily connect back to the vendor network. So it can if the vendor network is IP-based again and accessible from the internet, then you can connect your network to the internet and everything is fine. But what about other vendor networks? We'll now have a look at GPRS, and GPRS uses some network name access via the access point name. This is the APN, and apart from the normal internet APNs that are used by the general public for internet access, there are special APNs for private networks. You can actually make contracts with the network providers, and then you get a special APN that is just for you, and you also get a private network which you can administer yourself, and all devices and SIM cards that you bought with this contract will not appear on the usual APNs, but they will use those special APNs of your private network, and thus they will appear in your private network and not on the normal internet. So basically you want to use those APNs to access the private networks. The question is how to do this. So to join an APN, you have to authenticate yourself. You know that for the general public internet APNs, you usually don't even need a username or a password. You can just leave this empty and anything will work. That's because they use IMSI and GSM authentication. So your IMSI is the International Mobile Subscriber Identity. This is your ID. It's basically your ID for the network. So the provider knows who you are, and you are authenticated via the GSM authentication. So this is sufficient, and you don't actually need an additional username or password. Still, there is the possibility to use username and password authentication for special APNs, but I don't think it is very widespread. So you need a special IMSI and the according secret key to join this special APN. You will then be able to access this private network. So how can this be used, this information? One point is, of course, attacking the actual device and gaining access on the SIM card and the machine-to-machine module, and use this device to connect to the private network. And the second option is using man-in-the-middle with a root BTS and a patched cell phone. This basically looks like this, and here you have the machine you will let connect into your network, and your network is then connected to a usual cell phone that has GPRS support, and the cell phone then can connect to the vendor network, and you basically build a bridge to the original network, and the thing is, this needs some hardcore osmocom hacking, I think. So because you have to forward a lot of messages that are used for authentication and everything, you have to keep the states synchronous between the devices and the machine and everything. And saying GPRS encryption can actually prevent this. But as we've heard, saying GPRS encryption doesn't seem very widespread. So I haven't tried this, and I think it is quite some work to get this running, but it should basically work. So the next idea is attacking endpoints. Once you have access to a machine, you can hook it up to your PC, and then you can own this machine and control everything it does. And via this machine, you also get access to the vendor network, because you can do everything the machine usually can do. And that way, the network can be compromised by one of those rogue devices. And so we'll have a closer look at how to gain physical access to such a device. And it basically depends on how strict the packet filters between the machines are. And here we'll later have a bad example. So embedded devices are often proprietary devices. They are less complex than a PC, and they are designed for different goals. So mostly they are designed for low price. PCs might be designed for this too. Also fast time to market, availability, safety, and low power. You won't find safety and low power for most PCs, I guess, but the most important thing is that those embedded devices have security features from the 80s or so. That holds for most of the embedded devices, at least. For example, data execution prevention is some fancy new shit that you won't find in most of the embedded devices, because it's a long way to go there, and it hasn't reached the embedded devices yet. This creates a new problem, because the vendors, the makers, have to consider hardware security. They have to build a device that can withstand physical attacks on this device once it falls into the hand of an attacker. And this hardware security is quite difficult to realize. So let's have a look how embedded devices are usually constructed. to see some attack vectors on those devices. We have a microcontroller here that is usually has some integrated flash and some integrated RAM. So, but it's a single chip with integrated flash and integrated RAM. And in most cases, if you need IP stack, Linux or anything like that, you will need more flash and more RAM, and then you use some external flash and external RAM that is connected to the microcontroller. Also, you need some debugging interfaces, so the vendor or maker can download the original firmware into the microcontroller. This is usually done via JTAG or RS-232. RS-232 is the common serial port, and also you have peripherals that are connected to the microcontroller via some bus. So those three attack points are usually present when a microcontroller is present. The integrated flash and RAM is better secured than the external, of course. But the most important attack point on embedded devices are usually debug interfaces, because the debug interfaces aren't always disabled. So you can use them to gain access to the system, or you can reactivate them. And the bootloaders or the operating systems itself often have RS-232 access enabled. So all you have to do is connect this thing to a PC via the serial port and hit enter at the right time or something like that. And it will present you with a nice boot prompt or anything. And then you can modify the boot instructions. Everyone who has already bricked a wireless LAN router and flashed it or something like that has probably done this already. It's basically the same for other embedded devices. Another point is JTAG that can be used to access the system. JTAG can be disabled, but there was a nice talk at the 26th C3 that actually showed that there are some backdoors, some kind of backdoors in JTAG that can be exploited to gain access to locked devices and such things. Also, there are some hints on how to find JTAG, because here you have to find the right pinout for JTAG. And yeah, basically this can be done, and it is not very complicated to do. The tools are there, and I just won't go into more details here because there are better talks for this. So the next attack point is external memories. External memory can be dumped or modified quite easy. You can just solder out the flash chip, which has been done here. This is a flash chip from some mobile phone, I guess. I soldered it out with hot air reworking, made a tiny PCB, soldered it on this PCB, and then I hooked it up to a microcontroller. You can then dump the flash quite easily. In fact, most flash ICs that are used nowadays have the MMC interface, which is the same that's used for the MMC and SD cards. So you can just hook those flash chips up to an MMC reader and then dump it without having to program a microcontroller. Otherwise, a tiny microcontroller will do in most cases, so you don't need very much code to dump such flash devices. Also, you can buy for a few hundreds, you can buy complete readers, but you can also hack your own tools there. I won't go into more details here again, and let's have a look at the third attack point we had, the peripherals. So the most important peripheral regarding machine-to-machine is usually the GSM module or some kind of communication module. And here we have a microcontroller. We have a GSM module that is connected to the microcontroller via RS-232. This is again the serial interface. You can also find USB here, and connected to the GSM module is usually a SIM card that is used for user authentication and that stuff. And both of those arrows here is unencrypted communication. So the GSM and GPRS encryption is done in the GSM module, and once you have access to this bus, you can read anything and you can also modify this data. The same holds for the communication with the SIM card. And yeah, that's it so far. We will have a look at an example later. So the first example is actually a smart meter that uses Ethernet with SSL end-to-end cryptography to communicate with the vendor or the power provider. And this implies that the smart meter needs some secret key storage for the SSL encryption. And well, yeah, we want those keys, obviously. So let's have a closer look at this thing. I disassembled this thing physically. It was a test device, so yeah. Then the next point was I mentioned the debug interfaces, which are usually the first way to attack a device because they are more simple than memory dumps. And so I traced the RS-232 wires on the PCB, and you can actually find those wires quite easily in a lot of devices because for the embedded systems use a 3.3 voltage signaling voltage for RS-232, while the PC needs plus minus 10 volts. And there are some level shifters that are used for the level translation between PCs and embedded devices. And those chips are quite common. It's basically always the same in all the devices, and you can also find the data sheets for these chips. So once you have found this chip, you can look up the data sheet and you will see where the RX and 2X lines are and connect a PC. The problem was that there was nothing to be seen here on the serial port. Also, you can then brute force some baud rates and send some stuff to the device, but you don't see anything here. So I had another look at the other chips on this system, and there's a serial EEPROM with I2C bus, and this bus is also serial, and it uses two lines. It's quite easy to sniff. There are tools available, for example, the bus pirate, and I'll put the slides online later so you can just use the links and follow them to the devices. So using those bus pirate, you can easily sniff this bus, and you will see that some boot parameters are transmitted via this bus, and they are stored in a serial EEPROM. So you can also change the serial EEPROM contents with this bus pirate quite easy, and you can just modify the boot parameters. So you can re-enable the serial console there, and then you get an U-boot prompt. U-boot is the generic loader for embedded systems that use Linux. Yeah, it's okay. So the next point was to start Linux via U-boot, and here one can point the init process to the shell, and yeah, that's instant root, and one gets the private keys by just reading the right files. That's it. It's a walk in the park. So let's have a look at the next device. Now, there's a short roundup of this analysis. So what weaknesses were there? There was the unencrypted flash memory in the device, but we didn't touch this. It was not necessary because the debug interface was easier to attack, and there's no internal flash in the device, so it's also not possible to encrypt the external flash. And so I used RS-232 debug to reactivate this thing, and the secret keys could be dumped. The impact, however, is limited, which is basically a good thing, because just a single device was compromised and the secret keys dumped, and it didn't affect any other machines of the same make and model, because of the individual secret keys of the device, and there also was no VPN access, just a single SSL connection to the server. So one can transmit some other data here, but that's it. So the impact isn't that dangerous. Okay, another machine-to-machine device is a GSM-based machine-to-machine module from some motor vehicle. I bought this thing on eBay. Another good place is to look around for those things, junkyards and such stuff. So one can often get those things from broken machines. And I had a closer look at this thing. Here is a similar module that is probably not from a motor vehicle, but you can see some stuff there, for example, the antenna. And this here, this white thing is the actual GSM module, and it is mounted onto a support PCB. The support PCB provides the SIM card slot, so the SIM card is inserted into this slot here, and there's also some voltage regulation for the GSM module and some pin header conversions. So those GSM modules, you find the data sheets for those GSM modules on the internet. They are public usually, and in most cases they don't have an integrated SIM card slot, so such kind of support PCB is necessary in most cases. So in the device I got, the SIM card was present, but the SIM card was pin protected. So, but once you power this device up, it sends the pin card to the SIM, and I just sniffed that thing, which is quite easy to do using a simple microcontroller and a few lines of code. Or there's another tool from the Osmocom guys who do the open source GSM. This util is called SimTrace. It has a lot of fancy features, and you can even buy it here at the camp. And there was a workshop today, so yeah, the point is, pin cards, pin numbers of SIM cards are easy to sniff because this is no challenge response thing. They get transmitted over the bus in plane. And once you got this pin number, you can use the SIM in another phone. And in this phone, I patched the firmware to the original IMEI of the machine-to-machine module, so the network won't see I'm using this SIM card in another phone. And yeah, I made a phone call with that SIM. I was a bit surprised that this would work because in the normal usage profile, this thing should not call anyone, I guess. However, the SIM was still active then. And so time to mess around with this a bit more. I put the SIM card back into the original GSM module and hooked the original GSM module up to the PC via USB. Those GSM modules have usually USB and RS-232. I mentioned that, and once you have the data sheet, you can just hook up a USB cable to this thing and connect it to the PC. There, thanks to the modern Linux drivers, you have some fancy dev TTY ACM where you get an AT command interface. And so you can issue AT commands to this module then. And there's this great command, atcg.gcont. And here, this link is an AT command list, so I'll put the slide later online. And if you ever need it, you can have a look at this there. So I used this command to show the APN, and of course I was hoping that I find a special maker APN, and I got this. So it wasn't general public internet, but it was my card to a private network of the maker. And next thing, of course, was to activate the IP interface, fire up the PPP stuff, and I got an IP in a private range without internet access. And without internet access, well, I started pinging some IPs, and some of those IPs had round-trip times of several seconds, and they had rather large variations in the round-trip time. And this implies somehow that those IPs are actually moving vehicles. Yeah, this made me a bit nervous, and let's stop here at this point and have a look at the roundup. So the weaknesses were that on the device side, the PIN number can be sniffed, and on the network side, there was a quite generous packet filter configuration, which allowed me to ping other devices. And obviously, there also was no root device detection because, again, after the voice call, the next thing those modules aren't usually designed for is pinging other devices, I guess. Again, nobody noticed this, it seems. And so, well, the attack was hooking up the machine-to-machine module to a PC and then connect to the vendor network. Again, this was quite easy, and the impact is somehow frightening, I would say, because one gets extensive access to the vendor network and can try to break into other things there. So for the hackerspace program, we obviously need some sane machine-to-machine security. So I thought about some mitigation strategies, and based on the previous finding, the question I wanted to answer is what can be done here? And there were two attack vectors that we exploited. The one were the communication channels, and the other one were physical attacks on the devices. Here in my examples, I only had physical attacks on the devices, but we need to consider both attack vectors. The first one, the communication channels, are, at least in theory, rather easy to secure, because there's this single point you have to take care of. Never trust the communication channel, and always add an extra and sound, that means encryption and authentication layer for all the data you transmit over a communication channel. And by sound, I mean well-reviewed and not something like this GPRS stuff. So for this extra encryption layer, you need some secret data that is stored in the devices. And here things get more complicated, because the embedded devices have to be secured. And the basic idea is, of course, to protect the secret device, the secret data within the device, so an attacker cannot access this. And the first thing to do is obviously to disable all debug interfaces and prevent re-enabling this. The next thing is to use internal memory of the microcontroller for secret data. So an attacker has to open the chip and opening a chip is another thing than just soldering out the chip and putting it into a reader. And one has to take care that no unencrypted secret data is ever transmitted over external buses. For example, if the PIN is transmitted in plain text, that is no secret data. And you cannot rely on the PIN as a secret, as some kind of security feature. The next thing is tamper detection is a nice feature here. So if the device is able to detect that it has been opened, it should delete its private keys and such stuff. This is done for some high-quality encryption modules and banking stuff and such things. It is more difficult for normal embedded devices, so this maybe is not really an option if you have to design some low-cost systems. Anyway, hardware security is difficult and expensive. One should try to do its best to get this thing secure. Still, one has to accept that those devices can and will be compromised. So you cannot control who has access to this machine-to-machine modules. Earlier or later, some devices will be stolen or something like that. And so the best thing to do here is really accept this and take care that the impact is limited for an attacker who has access on this on such a device. And this is early detection of rogue devices. This can be done quite easily because the behavior profile of such machines are usually very limited. For example, talk to a server, deliver some values, fetch some new values, some new firmware or so, and that's it. Those devices shouldn't ping other devices in most cases, and stuff like that. So this is quite easy to realize. You just monitor the devices for unexpected behaviors, and then you know if a rogue device is in your network. And the next thing is limit the impact of rogue devices. So if it is not detected, one can limit the action range of this particular device by with packet filters. It's so simple, basically, because those devices, again, because of their well-defined action profiles, they only have to talk to some servers or something like that, and you can block any other communication with the packet filters. This is basic network security that's been here for years. And the next thing is you can combine both, because you can monitor violations in the rules of those packet filters, and then you get your rogue device detection for free. Also, device individual secret keys really makes sense, because if all those devices have the same secret keys and one gets hacked, you can also, all your other devices are broken as well. So this is a very important step to limit the impact down to a single device that has been hacked. You can just blacklist this thing, throw it out of the network, and that's it. So the summary is that currently machine-to-machine security is rather hard to find, and we have identified some problems, and some mitigation strategies have been discussed here. So what needs to be done? The problem is that manufacturers need to start to consider security for those machine-to-machine scenarios. And also, I think the network operators don't really provide very much help regarding machine-to-machine security to their customers. I know this is basically the fault of the customer, but the network providers should know, and it's their customers, so they can at least, I think they should do some, give some information about those problems to their customers. I don't know if that is done in some form, but so somehow the awareness for this is missing, and this is a huge problem, I think, because the impact of those devices, once they behave malicious, is of much greater importance than a PC. So they can actually harm people, and I don't know of any machine-to-machine security initiatives to raise the awareness of those problems. So that's why I basically made this talk to raise this issue. And I think I'm done here. So.